have to see from potential difference to basically work done. Okay. So suppose there are 2 points A and B. Okay. So this is point A and this is point B. It is given that a test charge Q1, point charge Q1, is moved from potential from point A to point B. Okay. And let us say we are taking it in this way. Right?
Yes, sir.
So basically, yesterday we said that the change in potential actually by definition only will come out like this. Is change in potential energy per charge, which is the test charge. We can say in this case it is Q1. And we are taking this charge very slowly. So basically by taking it very slowly, we are making change in kinetic energy to be zero. Even if I don't take it very slowly, if suppose I start off initial velocity as zero, maintain any velocity in between, any speed in between, but make sure that my final velocity is zero. Even in that case, from point to point, I can see that my change in kinetic energy is zero.
Yes, sir.
Ultimately, we have to ensure that my change in kinetic energy from A to B is zero. Either the case can be we are moving it very slowly, we are moving it with constant speed, or we are varying it however I want, but my initial velocity and the final velocities are zero.
Yes, sir.
Okay. Now, if that is the case, I can say my work done is equal to negative of change in potential energy.
Yes, sir.
Which potential energy are we talking of over here? Electrostatic potential energy. And I have used a minus sign. So what should be this work done by whom?
The external agent.
No, by the I told you we discussed the reason I mentioned it here is we discussed one lecture specially on this, and that is a very important concept. I told you that work done is equal to change in potential energy happens when there are no changes in other energies, and the negative of change in potential energy comes when we are talking of the same source.
Yes, sir.
The work done by the electrostatic force is equal to negative of change in potential energy of electrostatic potential energy. I told you every force will have a potential energy of itself. Potential energy is not defined for just one particular force. Potential energy is only telling us the representing the potential factor of that particular system, that particular type of force. Electrostatic, gravitational, magnetic potential, right? So we can have potential energy irrespective of what the force is. It can be gravitational force, electrostatic force, magnetic force, or an external agent.
Yes, sir.
Is applying a force. So basically, we can talk of potential energy of Tom, like Tom's potential energy, just like electrostatic potential energy. Correct? And I told you that whenever there is no minus sign over here, then these two subscripts should be opposite. In that case, we will get external agent. Okay. Fine. Anyways, so the point is that I can write the change in potential energy as negative of work done divided by the test charge.
Yes, sir.
Therefore, the work done by the electrostatic force is equal to test charge negative of test charge into change in potential. Okay.
Yes, sir.
In this story, this is the initial point, this is the final point, is equal to minus Q1 into change in potential should be final potential minus initial potential.
Yes, sir.
So it should be VB minus VA.
Yes, sir.
Now, if I take the minus sign inside, I can say work done by the electrostatic force is equal to Q1 into VA minus VB. Is this clear?
Yes, sir.
Just for an example, there is some kind of a field in the downward direction and uniform field. Okay, uniform field in the downward direction. If my field lines, that two uniform field lines, are vertically downwards, how should my equipotential surfaces or equipotential lines look like? If these
They
are,
should be perpendicular.
they should be perpendicular, horizontal. Because correct. If because these are vertical, I can say any sheet which is in the horizontal plane represents the equipotential surface. Correct?
Yes, sir.
Next.
This is electric field, right?
Good. I didn't mention the name.
Sir, you just get field.
No, I said field. Then I said equipotential surface. But I don't know why I did not mention.
Which field?
Yeah. I just Rajni, I don't know why I did not mention the name of the field, but let us see what we are trying to do. Okay.
Okay.
Happy?
Yes.
Let us see. Okay. Now, here I have a potential of V1. Here I have a potential of V2. And basically, let us say I can draw the equipotential surfaces in this way, right?
Yes, sir.
Horizontal and perpendicular to the thing. So we'll say let this be P2, correct?
Yes, sir.
Now I will mention if I'm talking of electrostatic field or if I'm talking of gravitational field. If it is electrostatic field, if I place a point test charge plus Q over here, will the test charge fall down or go up? We said a uniform electric field exists in the vertically downward direction.
It should fall down.
It should fall down. In place of a point mass m, and if this is a gravitational field that is in the downward direction, then should that point mass fall down or go up?
Fall down.
Actually, if it is a gravitational field and we have a point mass, or if it's a electrostatic field, I'll write it over here. If it's a gravitational field and we are using our testing kind of a thing as a point mass, okay, or if it is a electrostatic field and we are using our charge, in both the cases, what are we studying? We are studying the motion of the particle, correct?
Yes, sir.
If I place a point test charge or if I place a point mass m, in both the cases I am seeing that it is falling downwards. Falling downwards means that I am studying the motion of the particle.
Yes, sir.
And the motion in both the cases is basically falling downward, correct?
Yes, sir.
Next, I can write the work done as negative of change in potential energy. Again, I'm not mentioning any subscript right now. In terms of electrostatics, I can write this as Q into delta V. Correct?
Yes, sir.
So this becomes E and E. Yeah.
Yes, sir.
In terms of gravitation chapter, work done by the gravitational field is equal to minus of change in potential energy, gravitational potential energy. And
Yes.
in place of charge, I will only have mass, but my delta V again will come to the same story.
Yes, sir.
So I said V1 and V2 over there. Because we are in electrostatics, I am doing electrostatics. If you're in gravitation chapter, he will give you mass is 10 kg, substitute M value. That's it. In electrostatics, take charge as 10 coulomb. In gravitation chapter, take mass as 10 kg. But the story behind it, everything is the same. Gravitation also is a field. Electrostatic is also a field. Gravitation also has a potential energy. Electrostatic also has a potential energy. The entire story is the same, right?
Yes, sir.
Now, so just doing for this fellow. So I will have work done by the electrostatic force is equal to minus of charge. See, delta V. We are going from up to down, right? So this is my initial point and this is my final point. So delta V should be V2 minus V1.
Yes, sir.
So I can write this as V2 minus V1, right? And if you take the minus sign inside, I can write work done by electrostatic force is equal to charge Q into V1 minus V2. Correct?
Yes, sir.
Can I say V1 is greater than V2?
Yes, sir.
Next, because the electric field is in the downward direction.
Hmm.
Right? Next point. If I place a point positive test charge, it will always go from higher potential to lower potential.
Yes, sir.
So the work done by the electrostatic force is also showing me charge into higher potential minus lower potential. Is this clear?
Yes, sir.
So just as an example, what is the question number?
31.
31.
Hmm.
So just as an example, if I take this, let the potential V1 is equal to 50 volts, potential V2 is equal to 25 volts. Obviously V1 should be greater than V2 because we are saying there is uniform field in the downward direction.
Yes, sir.
Or we are saying field is in the downward direction. That means above I'll have higher potential, below I'll have lower potential. Now if I place a point test charge of 10 microcoulomb anywhere, right? Let us say 0.1, it will fall down. So the work done by the electrostatic force. By the way, if I place the point test charge, is the electrostatic force doing the work or is there an external agent doing the work?
Electrostatic force.
The reason why I give gravitation is because it is easy to understand in gravitation perspective. If I drop something, gravity is basically pulling it downwards. In this case, in place of gravity, I have electrostatic field, but everything else is the same. Obviously, if I place a point test charge, the electric field will do the job.
Yes, sir.
And how much is the work done by that electrostatic force is equal to, I will do charge into higher potential minus lower potential. Simple.
Yes,
So
sir.
10 microcoulomb into delta V is 25 minus 10. Sorry, 50 minus 25, right?
50 minus 20.
50 minus 25, which is basically 25. So 250 into 250 microjoules. Is this clear?
Yes, sir.
Work done by electrostatic force is 250 microjoules. So can I say work done by external agent is minus 250 microjoules?
Yes, sir.
But there is no external agent only, no, in this question.
Yes, sir. Then they are not supposed to write for the extended.
Wait, I'll explain. Suppose if I am saying that I am taking it very slowly, is the only case where I can say that the initial and final kinetic energies are zero, making the work done as change in negative of potential energy, change in potential energy. Otherwise, work done will be change in potential energy, change in kinetic energy, change in any energy that is present.
Yes, sir.
When you drop it, it will attain some kinetic energy. For it to not attain any kinetic energy, an external agent has to stop it. And we did this story long
In
ago.
the
Another
yes, sir.
force of equal magnitude, irrespective of the force varying all the time. That external agent is also varying its magnitude all the time, making sure that the acceleration should be zero, right? All those stories.
Yes,
So
sir.
he might mention it, he might not mention it, but as soon as I'm using work done is equal to negative of change in potential energy, I am saying that the change in kinetic energy is zero. And
Yes,
change in
sir.
kinetic energy is zero. How is it possible? If I drop my marker over here, it will it will gain some kinetic energy, right?
Yes, sir.
Then where is that? If I am writing this, there is no change in kinetic energy. That means there is an external agent. There is no such surprise over here. Automatically, as soon as we write that, we know that there is external agent. Okay,
Yes, sir.
clear?
Yes, sir.
Very good morning.
What happened, sir?
Xerox. In the same example, if you see, if I have, suppose there is another test charge, let's say Q2 test charge, but I am taking this Q2 test charge from this point to this point.
Yes, sir.
I am taking it. Obviously, I will have to take it. It will not go automatically. Particle
Yes.
will fall automatically, but will not rise automatically. So from low potential to high potential, when I will go, work done by the electrostatic force, I should know that it is automatically negative.
Negative. Yes, sir.
And I will say it is minus Q2 times whatever is the low potential minus high potential, which is V2 minus V1. Is this clear?
Yes, sir.
Work done by the electrostatic force uh, is V1 minus V2. Because if it is V2 minus V1, then we are double doing the negative sign. Basically, this comes out as positive if we take Q2 charge as some 20 microcoulomb. So in this case, my work done is minus 20 into 10 to the power minus 6 into 25, right? Delta V is 25 volts.
Yes, sir.
So my answer will be minus 500 microjoules. This is work done by electrostatic force. But in here, if I want to find the external agent, it will be 500 microjoules.
Yes, sir.
Take this down. If a Q2 charge is, so you can do this as A bit and this as B bit. In B bit, what is the question? if a Q2 charge is taken from potential V2 to V1. If a Q2 charge of 20 microcoulomb is taken from potential V2 to V1, then the work done by work done by the electrostatic force is negative, but work done by external agent will come as positive. Magnitudes obviously will be the same. Hi guys, I hope you enjoyed the session. If you think this video was useful, don't forget to like, share and subscribe to my channel. Also, I'll be waiting for your comments in the comment section. See you in the next video.